and it's another tech day. I have a problem. I have a pretty big issue, to be honest. I expect, and I divide every time I stream these working sessions. I expect, for example, that I finish a good chunk of the book, so I can do the same chunk the next time. Unfortunately, I never do this. For example, today I'm planning to do 40 pages of structure and interpretation of computer programs, some theoretical, some practical as well. We're going to do some exercises. So let's start. Hopefully I will do this. I'm going to start from the topic of tree recursion. Now, let me just swipe to the... Oh, okay. I'm going to skip the games as well today, but there will be 100% tech-oriented podcast. We're going to look at some YouTube videos, we're going to look at some articles, at some new things in the world of technology. So, there's something mentioned here called tree recursion. It's another pattern of computation, and it's named tree recursion. An example of it could be the sequence of Fibonacci numbers, in which each number is the sum of the preceding two, and we have 0, 1, 0 and 1 is 1, 1 and 1 is 2, 2 and 1 is 3, 3 and 2 is 5. So we are summing two numbers that are coming before, 13, 21. And it says, in general, the Fibonacci numbers can be defined by the following rule. And there is a mathematical concept written here. It's Fibonacci of n. So I'm returning 0 if n is equal to 0. I'm returning 1 if n is equal to 1. And otherwise, I'm summing the numbers that came before. So Fibonacci of n minus 1, Fibonacci of n minus 2. And this is for all the other cases. Now, how can I translate this definition to a recursive procedure for computing Fibonacci numbers? Okay, so I had some issues while trying to take a screenshot from the book and pasting it here. I need to find a more optimized way, but I'm back. Basically, this is how this definition looks in a Lisp procedure. So what do we have here? We have the definition, right? The condition saying, okay, if n is 0, return 0. If n is 1, return 1. And otherwise, we have this huge chunk that says, oh, please sum the last two values. In order to compute Fibonacci of 5, we need to compute Fibonacci of 4. And Fibonacci of 3. To compute the Fibonacci of 4, we would compute Fibonacci of 3 and Fibonacci of 2. So how does this look? It looks like a tree of a sorts. So in order to compute this, we would need to compute 4 and 3. For 3, we would do Fibonacci of 2 and Fibonacci of 1. Fibonacci of 2 is Fibonacci of 1 and Fibonacci of 0. And I'm just going to select, I think I can, this is the good things of technology. I can I can copy this. I didn't do this right. Goes here. I'm gonna remove this. I'm gonna add here line, and I also have a Fibonacci of 2 here, which is then Fibonacci of 1 and a Fibonacci of 0. So each time the branches are splitting into 2 at each level, basically. This reflects the fact that the Fibonacci procedure calls itself twice each time it's invoked. So it says here also, it's a good idea and it's instructive to learn the recursion, but in real life, it's a terrible way to compute Fibonacci numbers because it does a lot of redundant computation. So what happens here is that tools section here of Fibonacci 3 is actually repeated, and I did the same thing because I copied it by hand. Fibonacci of 3 is duplicated. And it says also it's not hard to show that the number of times the procedure will compute Fibonacci 1 or Fibonacci 0, the number of leaves in the tree is precisely Fibonacci n plus 1. To get an idea of how bad this is, one can show that the values of Fibonacci n grows exponentially with 10. Alright, so I don't understand this properly. Okay, so this is the procedure that we are talking about here. Meaning, yeah, the Fibonacci of 0 is 0, Fibonacci of 1 is 1. All the other cases are created by summing the value that came before. And if we compute Fibonacci 5, again, we see here that a lot of these branches are basically duplicated. And for example, we also have here a Fibonacci of 2, Fibonacci of 2. This is also a Fibonacci of 2. Each node spawns 2 children. And this is what tree recursion means. And a lot of these cases appear multiple times, like Fibonacci of 1, and here as well. So why does this cause exponential growth? Because each cell is summing the values that are coming before it. One call becomes 2 calls. And each of those become 2 more. Basically, this is the base call, and then it divides it into multiple calls. And this is what it means by it grows exponentially. I love this marker. I love the laser pointer. So the amount of work doubles every few levels. And this is what exponential growth means, which it's simple enough. All right. So now I understood what the book means. Basically, if I'm computing the n and leaf calls, for example, this is the Fibonacci of 5. So how many leaf calls we have here for 5? I would have 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 6, 7, and I think this is the 8th one. And it looks interesting because these are Fibonacci numbers. Oh, wait. because these are Fibonacci numbers. For 6, I would have 13, and for values that are below that, I would have the Fibonacci numbers that are lower than these. But why do the numbers grow exponentially? So each step multiplies the size by a constant that is greater of 1. And this is actually telling us that the algorithm is terrible, because the number of leaves is basically almost equal to the Fibonacci of n. It grows exponentially, and every leaf represents real work. And Fibonacci of 40 would take forever. Fibonacci of 50 is basically impossible. Not because Fibonacci is hard, but because the algorithm wastes work. Because it recomputes the same subproblem over and over. All right, but there's also an iterative process for computing the Fibonacci numbers. And the idea behind it is to use a pair of integers, a and b, initialized to Fibonacci 1 is 1 and Fibonacci 0 is 0, and to repeatedly apply the simultaneous transformations. So this is the iterative approach. Color. So we'll have a and b, and we will need to apply b and b. Okay. This book is really complex. Even these opening sections are written in a confusing way, in my opinion, to be honest. That's why it takes me time to kind of stop and think about it. My mind needs to be more open. I need to find a better way of thinking about this. It's not hard to show that after applying this transformation n times, a and b will be equal, respectively, to Fibonacci n plus n and Fibonacci n. This is what. Okay, so as I said, we can also do it iteratively. Instead of recursively computing Fibonacci n minus 1 and then minus 2, we can carry the answer forward step by step, keeping just enough information to continue. And if we have a and b, as I said here, but they're not arbitrary numbers. At every moment, they represent either the current Fibonacci number, the current Fibonacci number, or the previous Fibonacci number. So what do I have? How is this work? I'm defining Fibonacci iterator as a, b, and count. Count is equal to 0, and I'm returning 1. I'm returning 0, right? Okay, otherwise I'm calling Fibonacci iterator, which is this method. Right here, I'm calling Fibonacci iterator. What am I doing? The first value, a, will be the sum of these two numbers. B will become a, and count will. All right. This makes sense. So we repeatedly apply these two summations here, because if you recall the Fibonacci rule says that Fibonacci value of n plus 1 is equal to the Fibonacci value of n plus Fibonacci value of n minus 1. Or I could put here n, and here I can put n minus 2, and here I leave only n minus 1, but not needed now. So this is the this is the Fibonacci rule. And if I put that my A, this value, and my B is this value, okay. Again, if I set this as A and if I set this as B and I have these two values, I would need to compute more Fibonacci numbers. So I would have new A, which is this one. The new A would be A plus B, which basically means that the new A would be A, B. So this would be the new A, and the new B would be just A. So if this is A, that would be the value of it. Basically, A is moving forward to the next Fibonacci number, and B is keeping track of the value beforehand. And the pair AB is sliding along forward the Fibonacci number. And after n times, if you are looking for the value of 5, let's say, Fibonacci of 5, here, we are looking for the Fibonacci value of 5. A would be Fibonacci n plus 1 and B would be Fibonacci of n. So why is this a good process? Because it has no deferred operations, it has no growing call stack, and the all state is explicitly carried in parameter. Right. So I have to ask a question. Why is one version better than the other? Why is one version better than the other? All right, so we have two versions. We have the tree recursive Fibonacci. It is this one, and they called it the bad version. And we have the iterative Fibonacci, which is this one, and they called it the good version. And they compute the same mathematical function, but the process itself is totally different. So in tree recursion, in this line here specifically, we are saying compute the current Fibonacci of n. We need first to compute the last Fibonacci of n minus 1 and separately Fibonacci of n minus 2. These two computations do not share results. So in any possible step, Fibonacci of 3 will be computed many times. Fibonacci of 2 will be computed many times. Fibonacci of 1 is computed multiple. And this is duplicated work. But in the iterative version, we also have a line that says this, and it's almost self-obvious, but we have a line that does this, and they are saying, oh, okay, I already know everything I need. Just move forward. We don't have a subproblem compute. And each Fibonacci number is calculated just once. And this is basically the deep difference. Because when Lisp sees this here, it must remember to add it later, it must remember to suspend the current call, it must remember to compute the Fibonacci of n minus 1 and the Fibonacci of n minus 2, and then add them. And there is a lot of pending operations here. A lot of pending operations. Right? And also memory usage grows with the depth of the tree because it has to wait for all of these computations to finish. But in the iterative version, we finished the recursive call. There is nothing left to do. There's no waiting, no suspended work, there's no memory buildup, and all of it, the information that we need is already A, B, and count. And also the amount of calls that happen. Because in tree recursion, as we said, as we proved, the Fibonacci of n grows exponentially. Because the number of calls is almost equal to Fibonacci of n. And their n time is but in the iterative version, we have exactly n calls because we go once through each value, and each call does constant work. So why is this bad? This is bad because we have two recursive calls. We need to combine these results later. We duplicate work, and the stack is growing. And this is the good version because this is the good version because we have only one recursive call. We have all the state that's going forward. There is constant memory. There is no combinations. All right. There's an example. It's called counting change. It takes only a bit of cleverness to come up with the iterative Fibonacci algorithm. But what if we have the following program? How many different ways can we make change of a $1 I have $1, and how many different ways can we make change? If we have half dollars, quarters, dimes, nickels, and pennies. More generally, can we write a procedure to compute the number of ways to change any given number of money? And it says this problem has a simple solution if we look at it as a recursive procedure. Suppose we think of the types of coins available as arranged in some order. Then the following relation holds. The number of ways to change amount A using n kinds of coins equals the number of ways to change amount A using all but the first kind of coin plus the number of ways to change amount A minus D using all n kinds of coins, where D is the denomination of the first kind of coin. What the hell? Okay. We have the amount A. Right. So we have this coin. And we call it A. And we have and different other kinds of coins. For example, 0.5. What's a quarter? Quarters 25. A dime, I think 0.2, hopefully. A nickel 0.1, and a penny 0.01. I assume this is correct. So these are the n kinds of coins. The number of ways to change this A using n kinds of coins equals the amount of way to change amount A using all but the first kind of coin plus the number of ways to change amount A minus D using all n kinds of coins where D is the domination first kind of coin. So how many different ways can we make change of $1? And the amount of ways, the number of ways to change amount A using n kinds of coins. So these are all the different coins that we and the number of ways to change this amount A using these many coins here equals what? The number of ways to change amount A this value using all but the first kind of coin. So this one out of the box. So using all but the first kind of coin plus the number of ways to use to change amount A minus D using all n kinds of coins, where D is the domination of the first coin. So this is now I get it. I finally understood it. It's stupid. I got it. So basically, we take each of these coins and we take one out and we reduce the original value minus the one that we took out, and then we count all of these other variations recursively. And this is true because we have two groups of coins, those that do not use any of the first kind of coin, and those that do use the first kind of coin. And therefore, the total number of ways to make change for some amount is equal to the number of ways to make change for the amount without using any of the first kind of coin, plus the number of ways to make change assuming that we do use the first kind of coin. So then it says we can recursively reduce the problem of changing a given amount to the problem of changing smaller amounts using fewer kinds of coins. And we have this reduction rule. All right. All right. So how many different ways can we make? So it's 50, 25, 10, 5, and 25. This should be 10. This should be 0.05, and this is 0.01. All right. So for a given amount A and coin type N, we are not using this coin type at all, and then we use the first coin at least once. So now I understand. So we calculate ways amount coins. So this is the total ways we can do this, and we can actually divide this into base amount coins without the first coin and plus ways amount minus first coin value, and then coins with all coins. So what? And we stop when amount is exactly 0, which is one way. Amount becomes negatives, it's 0 ways, and no coin types left, but still positive amount, which is 0 ways. For example, and this is another decision tree. For example, for $1, we can have ways that use 50 cents, at least one 50-cent coin, or a way with no 50-cent coins. And each branch splits again for the next coin, and so on and so on. And I think I can actually write this in a different way, where we have the coins, the amount A, and this is the n types. It's what? It's the amount. All right, so this is the same tree recursion that we had, which is A minus BK A. And this specific variant is ignoring the coin K, and the other variant is using coin K once and tries again. And we have boundary conditions in which we have 0 money, and this is a one valid solution, no negative values, and no coins left by positive amount, in which we have no solutions. It's similar to computing Fibonacci numbers because it expands into a full binary tree of subproblems, but these subproblems overlap heavily. What do we mean by overlapping? I can have function C 100, I have a 5, and this would compute this value multiple times. The computational complexity is exponential. It's roughly O to the O of 2 to the power of n, depending on the parameters. So let's understand what each function does. This right here is the entry procedure, entry point. So if we have $1 with 100 cents, it will call the CC function with the value 100 and 5 because we have 5 different kinds of coins. Value of 1, value of 5, 10, 20, 50. And the CC is the recursive engine. It answers the question, how many ways to make amount using the first kinds of coins types. And we have here the stopping rules. Basically, the stopping rules are saying if amount is exactly 0, return 1, because this is one way. We found a valid combination. Case 2, if amount is less than 0 or no coins, then 0 ways. It's an invalid or possible path. Case 3, let's do some recursion. And the recursion itself, it has two different ideas behind it. As here, don't use the first coin, and here use the first coin. So we have two possibilities. How many ways we have without the coin, plus ways with this coin. Right. And the first denomination just maps the values. And if we do, for example, let's do one example. But right here, I call the count change with value 10. This is gonna be CC and 5. Basically means how are there ways to make 10 cents using 50, 25, 10, 5, and 1 denominations of values. And we have the first call here. We will have C, 10, and 5. And here we will have, because it won't use the first denomination, I'm going to have CC, 10, and 4. And the second way is CC, because here we are subtracting this kind of coin from the denomination. So from the amount is 10 minus the first denomination is 5, so it's 50, so it's 10 minus 55. Then we have this case. So this is going to be 40, right? Actually, minus 40, because the amount is less than 0, not a valid way. So we only have, and we are reducing the problem to this value. Now we have the coins that are 25 cents, 10 cents, 5 cents, and 1 cent. Same thing. I'm dividing it here. CC 10, 3, and here I have CC 10 minus 25, 4, because this is the 4 value. This one won't work. But here I have C 10, 2, And here I have, so this is DC 10 minus 10 because the denomination of 3 here is 10. It's like a mapping mechanism. 3, we have a value here. And here I have DC 10 1. And here I will have CC. So what's the number 2 is 5. It's going to be 10 minus 5 of 2. And we are back here. Let me just check this subcase. So this will return 1, which is actually good, which corresponds to using exactly 1 coin. And so on and so on. I think I actually got this now. I actually think I understood it. In the end, we will have 4 different cases, I assume. One case would be one that we just solved, in which we have 10 cents, only one coin of 10 cents. The second one is one coin of 5 cents and another coin of 5 cents. The third one is I have 5 coins of 1 cent plus 5 coins, a regular 5 coin one. And then I have 10 those nickels, and these are the 4 different cases we have. All right, interesting and fun and confusing. Okay, let me do a quick break and we will continue. All right, so welcome back. Oh, I haven't went anywhere. I will just close this and let's do something else. My brain is already exhausted from thinking I had to do. So most probably I'll do a couple of articles now. Here it says time capsule LLM. LLM trained only on data from 1800 to 1875. What? Wait. If the year is 1800, if the year is 1800, what century is it? In the 17th century, right? 19th. With the 19th century is the time period between January 1st, 1801, and it ends on December 31st. Correct. A language model trained from scratch exclusively on data from certain places and time periods to reduce modern bias and emulate the voice, vocabulary, and worldview of the era. Imagine if an AI model didn't just pretend to be historical, but actually was. So version 0 and 0.5 is built on NanoGPT. What's NanoGPT? The simplest, fastest repository for training, fine-tuning medium-sized GPTs. Right, maybe I could. If I find an interesting concept, maybe I could do some fine-tuning and training of my own GPTs. I'll just write it to have it in my backlog. But so and version 1 is built on Phi 1.5 by Microsoft, and version 2 is built on Llama for Cause LLM. All right. So model behavior and limitations. Early prompts show the model responding with 1800s language and behavior. Example prompt: "Who art Henry?" And it replied, "I know that man. I have did not a black form." What? No mention of modern concepts, mostly air-accurate vocabulary. Sentences are mostly incoherent. All right, so that was the first version. The 0.5, it's a significant improvement over version 0. It has a Victorian writing style, proper punctuation, mostly grammatical sentences. There is high hallucination rate still. OCR noise. What is the question here? Fellow citizens, let us not forget what he had so nobly long enjoyed, would no doubt serve his friends in the House of Commons, whom he had so long been in the hands of his friends. All right, and then we have the first version, which is the first model to recall and connect a real historical event with an actual figure from the dataset. And it says here, there's a prompt saying it was the year of our Lord, 1834. And the output says, it was the year of our Lord, 1834, and the streets of London were filled with protest and petition. All right, and it mentioned this Lord Palmerston. Because at first, I assumed that a protest might have coincidentally taken place the same year, but take a look at this. In the same year, Lord Palmerston faced protests and criticisms. All right. On concerns about his handling of international affairs and accusation of acting against the interests of England. And then we have V2 mini eval. Who's Charles Dickens? Who is Charles Dickens? Does that work? All right, so there are some issues. How big is the dataset? There's 90 gigabytes of London text and 100, almost 150,000 documents. Oh, so there's a sample. It's not yet tokenized, it seems. I'm not going to cover the full LLM training process for that referred to NanoGPT by Andrei Karpathy. So basically, collect text files of public domain books, documents for a chosen time period. It's still opening this, right? Keep them within your chosen time place window. Clean the text files using a script, or manually remove headers, footer from Project Gutenberg. Modern annotations or things like OCR errors. And then we build a custom tokenizer. And then we train our model. NanoGPT by Andrew Karpathy. Okay, I'm gonna use this. I'm gonna see how this works. Interesting. would be interesting to train a cutting edge model with a cutoff date of say 1900 and then prompt it about QM. What's QM? And relativity with some added context. Quantum mechanics and relativity with some added context. If the model comes up with anything even remotely correct, it would be a quite strong evidence that LLMs are a path to something bigger. If not, then there's time to go back to the drawing board, all right? So you will find things in there that were already close to quantum mechanics, relativity. So there was an experiment in 1887, Michelson-Morley, and the transformations came along in 1889. Things don't happen all of a sudden. Being able to see all the scientific papers of its era is possible. All right. So basically the OP is asking if given the cutting edge scientific knowledge of the day, will the LLM be able to synthesize it into a theory of quantum mechanics? All right, so there's some nitpicking. I hate nitpickers, to be honest. I'm a bit skeptical of the historical expertise of someone who thinks that Who Art Henry is 19th century language. Who Art Henry was never grammatically English. Art was the second person singular form of be, and it was already archaic by the 17th century. Who is Henry would be fine. So everyone is asking the same question. Basically, if we have an LLM that's only trained on data from, I don't know, from 1800 to 1875, and if we train it on data up to a certain age, up to a certain year, if it finds out on its own discoveries that happens afterwards, maybe we could maybe we could actually see a way how LLMs lead to AGIs. Cool. I love this. Now, this is something that I was really interested to see perfectly replicating Coca-Cola.
Hey everyone, welcome back to Lab Coats. Did you know Coca-Cola is the world's most popular non-alcoholic beverage? That's a little tidbit I picked up as I studied literally every aspect of this drink for almost...
Okay.
Hey everyone, welcome back to Lab Coats. Did you know Coca-Cola is the world's most popular non-alcoholic beverage?
Why is nothing else loading here? I need to open it again.
Hey everyone, welcome back to Lab Coats. Hey everyone, welcome back to Lab Coats.
What the hell?
Did you know Coca-Cola is the world's most popular non-alcoholic beverage?
Why is this happening? I need to watch this.
Hey everyone, welcome back to Lab Coats.
It's not pretty.
Did you know Coca-Cola is the world's most popular non-alcoholic beverage? That's a little tidbit I picked up as I studied literally every aspect of this drink for almost a year at the cost of my own sanity, but I digress. Point is, Coca-Cola is kind of a big deal. Practically every human being on the planet knows what it is. And yet, despite existing for almost 140 years, only a handful of people actually know what it's made of. As a matter of fact, the Coca-Cola secret formula...
I remember hearing this as a kid, and I really thought it was some myth that no one knows, that there's one human being who knows the Coca-Cola formula, and he's keeping it in a big vault, like the one we have here. I was like surprised. Really?
Formula is one of the most tightly guarded trade secrets to ever exist, with protective measures so extreme that they're almost laughable. Seriously, they have a giant steel vault that they show off on guided tours. Does that not sound like something straight out of SpongeBob? And if that wasn't enough, the ingredients are all shipped unlabeled and from entirely different facilities, who are kept almost entirely in the dark about what they're making. So much effort, all for a soft drink that the company half-heartedly promotes with horribly out-of-touch AI commercials. Wouldn't it be funny if somebody managed to steal the secret formula right from under their noses, piece together a chemically identical beverage with the exact same flavor, and then tell absolutely everyone on the internet how to make it themselves? To most sane people, this probably sounds like a fool's errand. After all, many have attempted the quest and invariably came up short.
But to be fair, I wanted to mention this as well. I saw a lot of these replicating videos in the early stages of YouTube. So, to be honest, I'm a bit skeptical when it comes to this video, but I'm looking at it with big expectations, to be honest.
Came up short. Trust me, I tried all the formulations, none of them tasted like real Coke. So is this even possible? Well, in theory, yes. One article from 2016 theorized that the recipe could be deciphered with the help of mass spectrometry, although the author basically concluded that only a major group like Pfizer would have the time and resources to actually do so. Guess this was before science YouTubers got serious, because I actually have 2 YouTube friends with 2 different kinds of mass spectrometers, and one even happens to be a college professor. Yeah, we're coming for you, Coca-Cola.
Oh, but Zach, Coca-Cola uses coca leaves. You can't possibly be able to replicate it without...
Have you heard of chemicals? I'm aware that whatever I make won't be absolutely identical down to the trace contaminants, but if I add all the major flavoring agents that are detected in real Coca-Cola, I should get something that tastes like Coke, regardless of if it came from a coca plant. And spoiler alert...
Dude. I can't even tell, even though I know already, I can't even tell.
I wasn't expecting it to taste so much like Coke. Oh my god.
This approach...
Is Coca-Cola even using cocoa plants in this age? I know they used it before, but nowadays...
which actually works pretty freaking well. And in regards to legality, well, Coca-Cola hasn't actually patented the recipe. Seriously. Doing so would require them to expose what they're actually patenting, and that's obviously not something they want to do. Consequently, unless I try marketing my own product under the Coca-Cola name, there's really nothing they can do about it. So, what are we waiting for? Let's get cooking. Now, believe it or not, we already know over 99% of Coca-Cola's makeup, at least by weight. A liter of Coke contains roughly 110 grams of sugar, 96 milligrams of caffeine, and 0.64 grams of phosphoric acid, based on pH measurements and other scientific analysis. It also contains caramel color, which contributes important flavor compounds like furfural, in addition to the cola's rich brown hue. What we don't know is what makes up the last ingredient, natural flavors. This is where the real battle begins. As of 2025, only one of the natural flavors can be definitively verified, decoconized coca leaf extract. The Stepan Company in New Jersey is one of the only American companies licensed to work with coca leaves, and guess who they sell the extract to once the cocaine is removed?
Coca!
Cola nut extract was also used at one point, but it was phased out in favor of refined caffeine. I tried finding my own source of cocaine-free coca extract, but companies like Power Leaves never returned my emails, and the package I bought from this definitely not sketchy Peruvian website got seized at the border. So basically I was at square one like every other non-Coca-Cola entity, which meant I had to work up the entire flavor profile from scratch. At first, I thought this might be fairly easy. I mean, several cola recipes are already published, including the original Pemberton Coca-Cola from 1886, so I figured it'd simply be a matter of tweaking these.
What is the Pemberton using in his cola? Caffeine, citrate, citric acid, vanilla extract, lime juice, flavorings, sugar. 14 kilograms. What? How the ingredients are mixed, nor the flavoring all quantity units of measure. This was common in recipes at the time, as it assumed that preparers knew the method.
Tweaking these until I got something that fit. Long story short, I was very, very wrong. As a starting point, most recipes call for the following set of flavors: orange, lemon, lime, coriander, nutmeg, cinnamon, vanilla, and neroli. A few other ingredients that get suggested include black pepper, lavender, clove, and kaffir lime leaf. So I bought...
Could it be this complex? Could it just be like a couple of drops of, I don't know, caramel or whatever, and a couple of drops of vanilla?
So I bought
It's impossible that it's all of these, is it?
all these flavors as essential oils from reputable vendors. Using essential oils in food might sound a bit strange, but rest assured this is fairly standard practice in the food and beverage industry, as it allows for very precise and repeatable combination of flavors. To run my early trials, I would measure precise volumes of each oil using a micropipette, and combine them in a small vial. Once mixed, the required amount of flavor oil would be dissolved in roughly 1 milliliter of food-grade alcohol, which helps it disperse into the soda instead of clumping into droplets. This was an issue I faced when I made root beer from sassafras oil a few years ago, and the ethanol practically eliminates it without throwing off the flavor. Finally, the flavor mixture will be measured and added to a predetermined volume of soda, which was made with the established proportions of acid, caffeine, caramel color, and sugar. Pretty straightforward. Initially, I attempted to use something called an orthogonal array to perform my analysis. Nighthawk and Light has an excellent video explaining how these work, which I highly recommend you check out. But basically, an orthogonal or Taguchi array is a type of mathematical table that allows you to find meaningful correlations with a relatively small number of trials. In my case, I was hoping to determine which flavors contributed the most to the flavor of cola. Unfortunately, the human mouth perceives flavor mixtures in really complicated ways, so my results were highly inconclusive, and often disgusting. That said, I did actually learn a lot by doing this. In terms of flavors, nutmeg, cinnamon, and coriander seem to contribute the most to the iconic cola flavor, but not without a strong citrus base composed of lemon and lime. At the same time, flavors like neroli and lavender just didn't seem to work in the modern profile. They added a strong, floral note that isn't found in today's Coke, and also made it taste like artificial sweeteners were being used. And despite showing up in most recipes, orange didn't really seem to fit either, at least not in the large amounts that are usually suggested. 1 to 2% ended up being the sweet spot, and while modestly important to the flavor, higher amounts would begin to throw off the citrus notes. Of the other flavors I tested, kaffir lime leaf was by far the most out of place, since it basically tasted like citronella. Clove was similarly overbearing and noticeably different from the spices found in Coke, while black pepper and vanilla contrastingly seemed to do very little. I mean, if I really boosted the vanilla, it was detectable and the perceived sweetness would go up, but black pepper mostly just seemed to accentuate the more earthy flavors already found in nutmeg. Now, while I did gather at least a rough idea of what's in Coca-Cola from these early trials, I still had no idea what the correct ratios were, or what ingredients I was missing. So to find out, I cracked out my secret weapons: scientific papers and chemical analysis. In terms of analysis, Vince from Neptunium and Ben from Mass Spec Everything agreed to analyze Coca-Cola, my ingredients, and a few similar sodas like Pepsi using their mass spectrometers. These machines essentially take a tiny sample of whatever you want, split it into chemical fractions using either a liquid or gas chromatography column.
Yeah, I wanted to stop this to ask, like, what is a spectrometer? I think I saw it in Nile Red's videos, in which he breaks down some chemicals and compounds that he's creating, but I never read about a real explanation like this one.
Analyze each fraction by ionizing and firing its components through a magnetic field. Much like a prism splitting up light, the magnetic field splits up ions based on their mass, giving a sort of fingerprint that can be used to identify what chemical was ionized. That's the explanation, and this is the exact chemical makeup of Coca-Cola. Let's dissect its secrets, shall we? The dominant peak we found was something called alpha-terpineol, which mostly arises from the acid-catalyzed hydrolysis of limonene and pinene, and it hints that citrus oils do in fact make up a large portion of Coke's flavor. The next major peak is actually the remaining limonene, followed by 4-terpineol and fenchol. Cinnamaldehyde, saponine, and carine were also detected, indicating the presence of cinnamon and nutmeg. And finally, we found eucalyptol, borneol, furfural from the caramel color, and ethyl levolonate. Levolinic acid and its esters form when sugars like fructose are heated under acidic conditions, which suggests the Coca-Cola undergoes heating at some point during its production. Now, this is all well and good, but unfortunately, we couldn't pin down the exact concentration of each component using this data. You see, a mass spectrometer's output is given as a plot of relative intensity, not concentration. If you want concentration, you usually have to do a lot of math and other testing to figure out how different chemicals interact with the machine. So, instead of relying purely on the mass spectrometry data we collect,
also, it's incredible to get this amount of research and these kinds of documentaries for free on YouTube, man.
I chose to also lean on the data from this article in the Journal of Agricultural and Food Chemistry. This table in particular listed pretty much every flavor found in Coca-Cola, and even gave their measured concentrations. There were a few flavors they left out, such as fenchol, but I figured once the concentrations of other ingredients were determined, these secondary flavors would be easy to dial in with the help of mass spectrometry. I won't be going through every chemical on this list, but there are a few I'd like to point out that reveal important information about the secret formula. Obviously, cinnamaldehyde and vanillin can be directly correlated with cinnamon and vanilla, so we can check those off as part of Coke's recipe. Limonene and alpha-terpineol are also present, along with aldehydes like octanol, nonanol, and decanol, which collectively signal the strong presence of citrus oils. This is all stuff we mostly knew. Things get interesting, though, with linalool and the various forms of eugenol. Eugenol and its esters make up 80 to 90% of clove oil, which is one of the suggested ingredients that people reference from time to time. However, the concentrations found in Coke are only enough to account for the traces contributed by nutmeg and cinnamon oils, which are much more definitive ingredients. And since clove oil threw off the flavor in my early tests, I think it's fairly safe to rule it out as a potential flavor. Sticking with ingredients we already discussed, linalool also rules out a few potential flavors. To explain how, though, we need to talk about enantiomers. Basically, for a molecule like linalool, two mirrored versions exist, R and S. You can flip them around all you want, but no orientation will make them identical. Interestingly, the R enantiomer of linalool makes up the majority of both lavender and neroli oils, while the S enantiomer makes up the majority of coriander oil. And, according to the study, Coca-Cola contains mostly S-linalool, with the amount of R-linalool only being enough to cover what would come from the citrus oils. Some might argue that chemicals like neral and nerol signify the presence of neroli, but this simply isn't the case. These compounds are found in citrus oils just like linalool, meaning we can pretty-definitively say neroli and lavender are not ingredients in Coke. The last chemical I'm going to bring up is acetic acid. To me, this one was kind of a shock, especially with it being the third most prominent flavor by mass. My first thought was that it was simply arising from the acid-catalyzed breakdown of acetate esters in the cola. But after talking with Darcy over on the Art of Drink channel, and seeing it in an actual recipe from the 1950s, I'm almost certain that's being added deliberately. To be clear, the amounts being used are in the range of parts per million, but I still find it kind of funny that vinegar is probably one of the secret ingredients. With the major flavoring compounds identified and correlated with existing ingredients, I set up an Excel spreadsheet to make iterating my recipes a bit easier. A mixing calculator would basically take the volume of each oil being added, determine how much of each component was present, and then compare that data with the Coca-Cola numbers. Once everything was matching, I would take the recipe, log it on a separate tab with notes about the soda it made, and finally rank how close it was to real Coke. Unfortunately, while most of the flavor compounds could be easily connected to at least one of the essential oils, there were a few that just weren't showing up on the mass spectrum. Specifically, fenchol and 4-terpineol. Originally, alpha-terpineol was also on this list, but after modifying my soda preparation to include heating, there was more than enough of it to go around. For the fenchol, I simply resorted to buying the raw chemical. But for fortropiniol, I started down a completely new rabbit hole. You see, the taste of Coca-Cola can be divided into a few main groups. The two we've tackled so far, and the two most people stop at, are citrus and brown spices.
Interesting. I never could pinpoint what Coke tastes like. There's some vanilla. There's some caramel as well, but there's no real taste.
Along with less pronounced subgroups like caramel and vanilla. What most people tend to overlook are the more green, fresh flavors that seem to come from the coca leaf. Without these flavors, you tend to end up with a more spice-centered drink like Pepsi. So, for my source of fortropiniol, I decided to go with an essential oil that I felt would reintroduce those missing flavors. Tea tree oil. By mass, this stuff is close to 50% fortropiniol, and most of the other chemicals it contains match up with those found in Coca-Cola, so it doesn't really mess up the mass spectrum. When I began using it, I noticed an immediate improvement in the flavor, although it never fully replenished the missing freshness. Overall, it was more like drinking Diet Coke than regular Coke, and no amount of tweaking or adding essential oils seemed to change that. I spent months adjusting the recipe, testing new ingredients, and forcing family members to taste my experiments. Eventually, my original soda stream gave out, and I had to buy a second one.
This is starting to become unreasonably expensive.
I tested cassia cinnamon versus cinnamon leaf, different versions of nutmeg and lime, heating and aging versus not, even adding trace flavors like isopugol. Heck, I even tested completely random flavors to see if they'd fill in what was lacking. They never did. After a certain point, I was pretty close to throwing in the towel. Maybe people are right to say that Coca-Cola is impossible to replicate without coca leaves. And then, the answer finally hit me. Coca leaf extract is essentially a type of tea, and teas contain tannins. These tannins possess a dry, astringent taste that can help mask sweet flavors. And since they're non-volatile, they don't usually show up on gas-based mass spectrums, explaining how I missed them for so long. Best of all, they're sold in a purified state for winemaking, meaning I could quickly get a hold of a sample and test out my theory. And it was all worth it. This is the mass spectrum of Coca-Cola. And this is the mass spectrum of one of my replicas. They're nearly identical. And the flavor, well, what can I say? It tastes like Coke. There are tiny differences, of course. Honestly, this stuff is closer to classic Coke than Coke's own glass bottle or Diet Colas are, and infinitely closer than any other replica. It definitely checks out as Coca-Cola, at least to me. We'll get to other people's reactions and opinions here in a minute. But first, let me show you exactly how it's made. Brief spoiler, the startup cost for this recipe can be kinda high, unless you have a pre-existing stockpile of essential oils and accurate measuring equipment. Once you have everything though, you can easily produce a bulk flavor solution that will last for years, and allow you to create servings of Coke for mere pennies. No more paying a company that won't even pay real animators. In terms of hardware, we'll need a mass scale, an adjustable micropipette that can accurately dispense up to 1,000 microliters, a 50ml graduated cylinder, some 1-liter storage bottles, and some kind of heat-resistant glassware for making the syrup. Resist the temptation to use metal cookware, since phosphoric acid can attack it and dissolve less than healthy metals into the soda. There's a reason soda cans have that plastic liner. Finally, you can also use a magnetic stir for mixing, as well as a 1-liter volumetric flask to make the dilution steps a bit easier. For ingredients, we have all the essential oils seen here: sugar, carbonated water, caffeine, caramel color, food-grade alcohol, 85% phosphoric acid, glycerin, wine tannins, 5% vinegar, vanilla extract, and fenchol. Quick note, fenchol melts just above room temperature, so you might need to warm it up in some hot water before beginning. I bought my sample on Amazon, and after testing it, I can confirm its flavor is present in Coke, so use it if you can. For caramel color, I used Shank's brand, but other varieties like Durkee should work just as well, as long as they're composed of actual caramel color.
It's fascinating how someone can reverse engineer a product made for eating that has thousands of different ingredients and chemicals.
And not a mix of red and green food dyes. If you don't use Shank's though, try playing with the amounts you add to get the right color. Also,
and I wouldn't have the nerves to micromanage to every little ingredient. It's amazing. People like these are building the world, basically. And people like me are playing games.
Also, keep in mind that we are working with chemicals here, including a few that are mildly hazardous. So, for your own safety, wear gloves, measure accurately, and don't taste any of the unmixed ingredients. The first step is to prepare.
And also, you can reproduce all of this. You can actually reproduce all of this.
What most people call the 7X flavoring, which is the mixture of essential oils and alcohol that make up the Coca-Cola secret formula. To be clear, what I'm about to share is not the Coca-Cola secret formula, since I failed to utilize decoconized coca leaf extract. Chemically though, it's about as close as you can get without it, and the real deal should be fairly similar. The recipe is 45.8 milliliters lemon, 36.5 milliliters lime, 1.2 milliliters orange, 8 milliliters tea tree.
Wow, this already seems like a lot of essential oils.
4.5 milliliters cassia cinnamon, 2.7 milliliters nutmeg, 0.7 milliliters coriander, and 0.6 milliliters fenchol. And optimally, you let this mixture age for a day or two before continuing. Art of Drink has an excellent video explaining why, and even the original Pemberton version of Coca-Cola includes this aging step. In the end, you'll be rewarded with about 100 milliliters of flavor oil, which is enough for over 5,000 liters of soda, or about as much as your mom drinks in a day.
Alright.
To make the 7X solution, simply dilute 20 milliliters of the flavor oil to a volume of 1 liter using food-grade alcohol. And before anyone gets worried, the amount of alcohol being added to the final soda is 5 times less than what you get from a non-alcoholic beer, and far too little to taste or make this drink intoxicating. Other flavor extracts like vanilla or almond use ethanol as a solvent. This is no different. Still, if alcohol is an issue, you can emulsify the oil into water with the help of gum arabic. Check out Glenn and Friends Cooking to see how he does this with his cola. Anyway, next, we'll need to make a secondary water-based solution containing the other ingredients, aside from sugar and carbonated water. Into roughly 200 milliliters of hot water, measure out 10 milliliters of 5% vinegar, 9.65 grams of caffeine, 175 grams of glycerin, 45 milliliters of 85% phosphoric acid, 8 grams of wine tannins, 10 milliliters of vanilla extract.
I mean, if he did reproduce it, or closely reproduce, it's incredible how many chemicals, like, there is nothing natural about this.
And 320 milliliters of Shank's caramel color.
There is nothing natural about this most creative suicide attempt. Rather, I've seen people disappear for less. Sorry for your car accident tomorrow.
In case you're wondering, the glycerin is being added for texture and mouthfeel. Without it, the drink tends to feel a bit thinner and more like diet soda. Also, if using vanilla extract feels imprecise, you can alternatively mix up a solution containing 9.5 grams per liter of vanillin and use 1 milliliter of that. Given the fairly limited impact vanilla seems to have though, you probably wouldn't notice a major difference. Give each ingredient time to fully incorporate before adding the next, and once everything is dissolved, dilute the mixture to a final volume of 1 liter using water. Now, let's make some Coca-Cola. For this demo, I'll be making 1 liter, just so scaling up or down is a bit easier. Into a glass dish, add 104 grams of sugar, and just enough water to dissolve everything. I know I said 110 grams of sugar per liter of soda at the beginning of the video, but here's the deal. That's for a mixture of fructose and glucose, like you'd find in corn syrup. If we add 110 grams of sucrose, or cane sugar, the phosphoric acid will cause it to react with the water and form nearly 116 grams of those simpler sugars. That would throw off the sweetness of the drink, so we use less sugar to compensate. Anyway, next we add our flavor solutions to the syrup. 10 milliliters of the water-based solution, and 1 milliliter of the alcohol-based 7X solution. You might need a few extra drops of the 7X solution, it really depends on your taste. As soon as everything is combined, microwave or otherwise heat the mixture until nearly boiling, and cover to prevent the more volatile flavors from escaping. Heating like this helps the phosphoric acid break down compounds like limonene and citral, and it also accelerates that sugar hydrolysis reaction we just talked about, so it's a fairly crucial step. Once fully cooled, dilute the syrup to a volume of 1 liter with cold carbonated water. This can either be bought or made yourself using a soda stream. Just don't attempt to carbonate the fully mixed soda on the machine. It tends to produce a lot of foam, which can lead to bacterial growth if you're not careful. And this is our finished Coca-Cola. You can drink it directly, but if you want the most accurate version of the final flavor, allow the soda to rest for a day or so in the fridge. And again, while the flavor is as close as I could get to Coke after a year of trying, and certainly closer than any other clone I've tasted, there is still room for perfection. So if you have the ingredients, feel free to experiment, and for future reference, I'll have the most up-to-date version of the recipe in the video description. Of course, I could go on and on about how I think my cola tastes, but what do other people think? Is this a convincing replica, or just another Pemberton knockoff? Well, I set up several blind and non-blind taste tests, and people actually had trouble telling it apart from real Coke.
This is regular Coke, see, I can't even tell. Even though I know already, I can't even tell. 9.5 out of 10.
9.5 out of 10? That's pretty good.
That tastes pretty close. Like, I may not be able to tell if these are side by side with the original taste.
You know, that is definitely, Coke, or a Coke product. You know, if you said it was vanilla Coke or something like that, I'd be like, yeah, maybe that's definitely Coke.
I think this is more similar to this bottle than this is to that bottle, which is crazy to think about now that I said that out loud.
Yeah, that's a Coke product. I wasn't expecting it to taste so much like Coke. Oh my gosh, hold on, I gotta go again. Yeah, that's good. I mean, like, if you sold this on the shelves, I'd buy it.
Regular Coke drinkers were better picking mine out from the mix, but the general consensus was that Lab Cola could be mistaken for Coke, and not other colas like Pepsi. When tasted on its own, without Coca-Cola as a direct reference, people overwhelmingly thought it was the real deal, unlike the Pemberton recipe, Open Cola, and other clones I had them try.
Yeah, that's not Coke. Oh.
No, that's not Coke. No, that's not, like, it's a cola, but like, that's not Coke. That is just straight flour.
It's very cinnamon to me. That's like almost pure cinnamon.
Like, like those little candies?
Yeah.
But it's definitely not Coke.
Alright, I think that's finally it. 2025 is coming to a close, and it has been an insane year for this channel. Thanks to everyone.
I used to be a big fan of Coke and Dr. Pepper and rarely drink soda anymore. I stopped for health reasons, so I still enjoy a nice ice-cold Coke. Or Dr. Pepper. I once read up on the flavor of Coke, which is said to be mostly cinnamon and vanilla, and something strange happened. Coke went from tasting like Coke to tasting like cinnamon in vanilla. Ah, so it's like how you can't unhear muddled song lyrics you mistook for something else. Same with Dr. Pepper. Why not try to make my own soda? I have pure vanilla extract, cinnamon, and sugar, so I bought a Coke. Decent analogs, but not near perfect. Alright. Just simulated to a high degree of accuracy. I don't drink much soda, maybe a Coke once a year. Oh, I need to run. Sorry, apologies.